going on. Just a quick overview of our mission again. We are going to be doing air quality testing. Our primary stakeholder is the Department of Ecology for the state of Washington. They want us to be collecting data on the carbon monoxide, nitrogen dioxide, ozone, sulfur dioxide, and particle pollution in the boundary layer around, which is between 300 and 3,000 feet. Some concerns from last time that we need to address. More information was wanted on payload, range, altitude, and sizing for our drone. All these specific values will be addressed in the rest of the presentation. Our budget has been elaborated on to cover the entire project instead of just our payload. Our Gantt chart was said to not have enough information, so we've added multiple steps such as modeling, prototype, testing. There were questions as to why we chose certain values for speed and range, and those will also be addressed in this presentation. It was recommended that we create a section for safety engineering. While we don't have a specific person appointed to this role, each person on the team has got safety in mind with their designs, and for example, some configurations we've been exploring we have chosen not to do from a safety standpoint. And we were also questioned as to why we weren't doing autonomous takeoff and landing, and I'm sorry if we did not make this clear, but we do plan on doing that. So finalized design requirements, we will be collecting the main data that the Department of Ecology wants, which is carbon monoxide, ozone, and PM2.5, which is particulate matter under 2.5 microns. They want this data between 300 and 3,000 feet above the ground, so we will have a hand-launched takeoff, a flight time of 1 hour, 2,500 feet with a max ceiling of 3,000, and a belly landing. A few driving requirements are obviously the hour flight time and 3,000 feet, but also the UAS shall only occupy 24 cubic feet. Right now, it only occupies about 17.2 cubic feet with our design, so we are doing well in that aspect. Our payload, this is our standard flight control stuff here with PIXHAWK, Pitot2, GPS, telemetry information to transmit our data, and servos. Right now, the cost of this is about a little under $600 with a weight of 90 grams. We expect this weight to increase a little bit due to the servos not being chosen yet, because we cannot choose those until we have our control surfaces completely defined, but it will not increase a lot. Avionics, this will be what we will be using to collect our data. We will have an Arduino Uno with a shield, a carbon monoxide gas sensor, an ozone gas sensor, a PM2.5 air quality sensor, and cables to connect them all. The weight's going to be about 150 grams, and the cost is a little under $150. This aspect will not change at all. The ozone sensor and carbon monoxide sensors are attached via an I2 connection, and the PM2.5 sensor will connect straight into the PIXHAWK. This is just a little diagram of how everything's going to connect together with some pictures of our sensors and PIXHAWK. We also plan on implementing flight autonomy into this mission. We want to make a flight mode that bases the aircraft's route on the data it collects. So, for example, it will fly in a certain pattern and collect data, and as this data is collected, it will move towards a higher or lower concentration of ozone, PM2.5, or carbon monoxide. And this will really help with data collection for our stakeholder for events such as the wildfire events that happened this past summer. So that was a big point for them. They really want to be able to test air from the smoke coming from that.
Good morning, everyone. My name is Will Reithman, and I am talking from Clemson University over here. I am the CAD and manufacturing lead for our team. So for the trade studies that we ran, the team ran various trade studies in order to determine metrics such as the weight and the sizing of the wings and the power. The parameters on the left here were analyzed, and their effects on things such as the weight and the wing sizing were assessed. The way that we did this is you held each parameter was increased, while holding the remainders constant, and then we determined the effects that occurred from that change to ultimately size our aircraft correctly. The goal here was to find the parameter that had the biggest impact on the aircraft size, and then to optimize those parameters. These parameters and their values are shown on the right here in this table. With the aspect ratio of 7.5 was a big parameter. This is just an example of one of the trade studies that we ran that shows the effect of increasing the aspect ratio. You can see moving from an aspect ratio of 5 to 7, you see a lot of gains there. But then moving on to 7 to 8 to 10, those gains are diminishing. So that's kind of how we found the happy medium there with our aspect ratio of 7.5. So the team started exploring different possible configurations of the UAV, and then in order to find the feasible configurations. The main parameters that we used to assess these concepts were weighted in order to determine which parameters took precedence over the others. These parameters and their average weights are shown on the left here, and then the different configurations and the considerations that we went through are shown on the table on the right here. So in the top left is a open VSP model of our overall design that we're going with. I'll run through the table on the right here just real quickly. So we're looking at a high wing configuration, a conventional T-tail. We're going to have a tractor front mounted motor. The fuselage is going to have a outer fiberglass composite skin, which will be non-load bearing, with an internal carbon fiber truss structure. And then we're going to go with a single carbon fiber cylindrical rear boom. And then the payload, the sensors will be evenly distributed in the lower half of the fuselage. So we've decided to take on the challenge of a folding wing design. And so we have two options as of right now. Our first option is the one that we're leaning towards. This option has each wing backwards to become parallel with the rear boom. With this configuration, the wing loading will be dispersed between pins and crossbars that go through the entire internal structure. And then we have a second option where the entire wing as one unit will revolve around a single central axis in the middle of the fuselage. And this would also be, the loads would be dispersed through pins going through the entire structure. These are just a couple pictures of our 3D models, and the top one is in the flight position, and the bottom one is in the storage position with the wings folded back. And you can see those pins that came out that hold the wings in the flight position. So we have a couple contingency plans for our high-risk concerns. So our first concern is that we're not receiving proper air sampling data because of the propeller turbulence, because we have that front-mounted motor and propeller. And so we have a couple contingency plans here. One contingency plan would be a pusher configuration, which is shown on the left here in that open VSP model. Another contingency plan would be to put the air sensors on the wings so they're out of the turbulent airflow from the propeller. And the third would be to go with a two-motor system with the motors on the wings to also keep those sensors out of the propeller turbulence. Our second concern here would be that the deployable wings cannot sustain the wing loading. And if this is the case, then we will end up just making the wings completely removable. So our initial constraint, performance and sizing, we had an initial weight estimate, a takeoff weight of 13 pounds. And we were able to update this estimate once we found our finalized wing size, the materials that we were going to use, the volume of our structure and fuselage, the propulsion components, and the controls weight. So we have a new improved weight estimate of a takeoff weight of 10.72 pounds. And this lower weight will result in more power for the system from propulsion as well as a lower stall speed. And the table on the right here shows the different subsystems and their corresponding weights. With the largest will be the battery, the total structure, and then the wings, which will add up to the total weight of 10.72 pounds.
Here's just our preliminary flight envelope for our aircraft. We will definitely need to do more testing with this as our design becomes finalized, but this is what we have right now.
All right, hey guys, I'm Andrew Hopkins. I'm in charge of the systems engineering for Team Atmos. We're going to talk about our selection of airfoils now. We had about 8 airfoils that we chose because they all had low Reynolds numbers, which is going to help us increase our flight time. And from those 8, we threw them in a decision matrix. And the main thing we were looking at was lift to drag ratio, which we picked the Epler 397 because it has the highest lift to drag and also pretty high CL max and acceptable thickness for manufacturing. So in the bottom right corner, you can see a picture of this airfoil that we've chosen. And the sizing of the wing was determined based on an assumed 13-pound weight of the aircraft, which we've now shown that it's probably going to be lower than that. And we picked a span of 7.5 feet with a chord of 1 foot to help us achieve that 7.5 aspect ratio we talked about. And moving forward, we've got some further analysis to do, but this is our general wing sizing that we want to go with. As for the tail airfoil, we had to choose that as well, and we wanted it to be similar thickness and chord to our wing airfoil. So we went with the NACA 12 airfoil, which has 12% thickness at 30% chord. There's the picture of it. And this is pretty similar to our thickness and chord of the Epler 397, which we chose for the wing.
Onto the propulsion system we will be using, we kind of designed this from top down, starting with our constraint of a long flight time. So we initially chose just a high capacity battery at 16,000 milliamp hours, 15 volts, and kind of worked down from there. That ended up being our final choice. But a lot of trade studies were done between propulsion and the aerodynamics team with different airfoils, different battery and motor combinations to see which one worked the best. And this is the one that we ended up choosing. As you can see there, it's pretty heavy as expected, 3.5 pounds, and with a price of $350.
So under our weight and balance the aircraft, we split our aircraft into a few components. We've got the motor, the fuselage, the wing, and the tail. And we mapped out the center of gravity from the tip of the motor in inches and put it in this graph that shows the circles show relative weight. So a bigger circle is more weight. You can see the weight on the right side with an overall weight of 10.72 pounds. And this puts our center of gravity of the overall aircraft at 16 inches from the tip of the motor. So for the stability and control part, we had to pick multiple parameters, such as the position of the leading edge of the wing, the position of the leading edge of the tail, and the size of the tails. And what we did is we kind of matched these up. We put the leading edge of the wing at the same position as the center of gravity of the fuselage with its internal components, and we kept moving back or changing these parameters until we had a center of gravity that was in front of the neutral point, which gave us a static margin of 23% when our neutral point was 18.8 inches from the tip of the motor. So here's a schematic showing our aircraft with the center of gravity slightly in front of the neutral point. And moving forward, we're probably going to want to bring the center of gravity back to about 60 or 70% of the chord length, which will increase our stability. We can do this with our configuration because we've built it to add in extra space. We have 3 to 4 inches that we can move the battery front, forward, or aft, which will adjust our center of gravity a lot because that's the heaviest component that we have. So for control surfaces, we've got 2 ailerons, 1 on each wing. We've got a rudder on the tail and an elevator on the tail, and these should give us all that we need to control our aircraft adequately.
So our internal structure design here is going to be a truss structure. It's going to be from carbon fiber, most likely laser cut from carbon fiber sheets of about 5 millimeter thickness. We're going to bond these different pieces together with 3M epoxy as well as tongue and groove joints. And then in the areas of higher loading, we'll likely use hardware. These areas would be where the wings interface with the fuselage as well as the rear boom. We're looking to use carbon fiber wing spars as well as a carbon fiber rear boom. And as touched on earlier, rods will be going through the entire internal structure to hold the wings onto the fuselage. We're gonna break our fuselage into two sections. There's going to be an upper section and a lower section as shown in this schematic to the top right here. The upper section is going to house the battery, the avionics, and the propulsion systems. And then the lower section will hold the air quality sensors in a completely separate bay. And as Andrew just spoke on, battery location is going to be variable by about 3 to 4 inches fore and aft, which will allow us to fine-tune our CG balance. And then that bottom battery tray is going to be removable likely with the air sensors adhered to the bottom of it so that we can remove that and we can make any changes to those air sensors if necessary. And then this entire internal structure will be covered with fiberglass shell, and a rough drawing of the fuselage is shown in the bottom right here. And so our mission is centered around air quality data collection. So we want to make sure that the data that we're receiving is good. And so what we're going to do here is we're going to have an air duct in the front of the fuselage and then an exhaust in the rear of the fuselage at the bottom there on the right. And we're going to 3D print ducts to expand the flow of air as it comes into the fuselage, and this will help slow down the air so that our sensors can get good readings. And then, as spoke on in the last slide, that battery tray will be removable with the sensors adhered to the bottom of it so that we can test those sensors and make any changes necessary there.
On to some administrative things. Here's an updated schedule. That was a concern from last time, so we added more, such as sensor testing, FEA analysis, finalized design, prototype construction. We've also added the spring schedule there. There are only a few points on there, such as final flight testing, initial flight testing, finalized drawings, and construction, because we aren't really sure the issues we are going to run into there, but the schedule will be able to be updated as we move forward.
And on to our overview of our budget, we've got a total budget of $4,750. That's what we're estimating everything will cost. This includes a $2,000 structures estimate because we're going to be making a lot of it out of carbon fiber, which is expensive. And then our testing budget is at $1,000, which covers replacing parts that may be damaged during testing. But total, we're way under that $6,000 limit, so we're looking good. And so what we did is we did a risk assessment on all of our subsystems, and we kind of put everything in this chart you see to the right. And out of this, we figured out that our greatest risks are that our air sensors may not work because of too much turbulence caused by the propeller. So if they're not getting the right air, and Will talked about this earlier with the contingency plan, our plan would be to move the location of the inlet or go with like a pusher motor idea. And then the other greatest risk we have is that the loads on the folding wings may be too high with the pins that we have planned to put in there. So also our contingency plan with that obviously is to take off make the wings fully removable, which Will also talked about earlier. So with that, we'd like to take any questions you guys have.
Are there any questions for Team 7?
Can you hear me? Hello?
Hello. We can hear you.
Bronco Luckett speaking from Boeing. So I'm a little uneased about the fact that I haven't seen a correlation between the mission and the airplane architecture. I heard some good concerns, and I actually wrote a note about sensor being somehow obstructed by the propeller turbulence and any fumes that may come out from the electrical motor. So that is definitely a concern, that the sensor, based on the mission, should be exposed in a clean air, which somehow drives the configuration, and the propeller-driven configuration at the front of the airplane makes very little sense. I absolutely agree that the configuration should be reconsidered. That's too great of a risk to proceed with, because the basic mission is jeopardized with the configuration. So I wouldn't even consider that as a risk. I would consider that as a red flag and switch right away to the configuration where the sensors are either in the wing, which kind of make it complicated because wings need to be detached at some point. I would rather have it than the nose of the fuselage, which leaves the drone to be either a pusher-driven or two-motor configuration, which is probably not needed and too expensive. Secondly, I see that deployable wing. I'm having troubles to understand how is deployable wing crucial to the mission requirements. If this is if the mission is such that the drone needs to be deployed in a moment of great urgency with a short notice, I see why this deployable wing may have a place in the configuration. Look at the cruise missiles, they have a deployable wing, but this is because the way they're stored in the carrier. And so, again, I'm failing to understand why is deployable wing critical for the mission. And then I'm looking at the airfoil section. Now, I'm a structures designer, so I don't know much about aerodynamics, but I'm really surprised that the team has picked up a symmetrical airfoil for the wing area. I mean, I've done a lot of air modeling, and I have not seen any any radio control models of that scale with such a low speed and low Reynolds numbers with a symmetrical profile. Usually they would use a Clark Y or something similar to that. It may be okay for the tail. I having troubles going eye to eye. Why would that profile be adequate for the wing?
Can I interrupt you there for a second?
Sure.
So if you can see on slide 19, we are using the F4397 airfoil for our wing, which is not symmetrical.
I may have missed that. I'm sorry.
Yeah, no problem.
Then going to the fuselage architecture. Again, I'm just wondering why the team picked up a frame structure covered with a fiberglass shell. First, fiberglass is pretty heavy, and in this case, it's only providing aerodynamic benefits, so it does not contribute to any structural integrity of the fuselage. So you are with such an architecture, you are carrying the dead weight, which is going to reduce your performance and the flight duration, which may be critical for your mission. If I would have to choose, I would use a load-bearing monocoque. This fuselage can be 3D printed and at the same time integrate all the joints, with the wing and the tail boom. Again, I believe that with a frame architecture and the aerodynamic shell, this is not weight efficient. However, I could be wrong. This is just my opinion. And then I have only heard an explanation. I have not seen the actual wing architecture. I understand that the wing, I kind of understood that the wing skin should be, I'm not even sure now. I failed to see any details of the wing architecture. So those are my concerns.
Thank you for all that information. the quick note for the deployable wings configuration, that's mainly to satisfy the requirement of easily transporting the UAV, and it be very easy to set up for launch. As for the fiberglass configuration on the shell, we will definitely have to look into that. Thank you for that. And we will definitely be looking into changing the configuration for the sensors immediately. Are there any other questions and concerns?
Yeah, Tyler, from the team here. This is Scott. Addressing the wing construction concern from Bronco. First of all, thank you for your feedback. And yes, I missed putting exactly what our best idea for wing construction is at this moment. But we're looking at a solid foam core with carbon fiber spars, as Will mentioned, and then we'll have either probably a fiberglass laminate as the skin, because we should be able to do some of that in-house, or build all the wing at least for a mock-up at Purdue, so that we can save money on some of the more difficult components. So yeah, we did miss that. We were thinking fiberglass laminate, solid foam core with carbon fiber spar on the wing.
Just one suggestion. I would suggest you to go and have Google for something called D-Box. It's pretty much latest and the greatest that is used in the air modeling world, and it's a structure where first about 30% of the wing, like a leading edge up to the main spar, is actually a carbon fiber shell, and then everything else is pretty much just for aerodynamics, either a copper ribs or a foam core. Really efficient design, provides just efficient stiffness of the wing, but it's not weight inefficient, because having a fully encased wing in any composite may not be required for airplane with such a low specific loading of the wing. Just a suggestion.
Bronco, this is Greg. Did you say D-Box?
Yeah,
D-O-X?
D as in David. D-Box. It looks like a D, first 30% of the wing is virtually a shell, and then it's bonded to the spar, and that's the structural component that provides stiffness. And then everything else is just, aerodynamics, either a foam core or some hopper ribs. If you key in D-Box, you'll find the hits in Google.
Thank you. We are coming up upon the 30-minute time constraint. So thank you for those questions, Bronco. Sorry that we didn't have more time to answer any other questions, but in the interest of remaining on schedule, I would encourage you to jot down those questions, and you can submit them to me if you'd like to, or Kathleen, but we'll get your feedback to the students.